Hey guys, Mrs. Dan's here. So we are starting our new unit on exponential functions. We're on lesson 1. So if you could just turn to the first page and write down the objective. Today we will graph exponential functions. Since we're graphing, you do need those graphing calculators out. So if you need to hit pause, please do so and get those calculators out. You may begin the do now, but of course in this video I will go over it with you. So you should easily be able to do this do now. You should know function notation by now. What we see in letter A is that the input is 2. So we have to put it in. Where do we put it in? We put it in place of x. So to evaluate f of 2, I have to do 8 times 2 to the second power because our x value is in the exponent. Before we continue, let's just talk about what this function looks like, right? It looks different than any other function we've done. It is an exponential function. What makes it exponential is that the x is the exponent. We've never had a function where x was the exponent. So we do need to remember way back to unit 1, our polynomial unit, when we talked about our exponents. So we have to follow the order of operations and do 2 to the second power before we multiply by 8. So 2 to the second power is 4, and then that 4 gets multiplied by 8. So this answer is a 32. So f of 2 equals 32. Let's take a look at your calculator right now. And let's make sure we know how to enter this information in. So I want to do 8, I'm sorry, and use the parentheses to multiply it by 2 to the second power. Now I just want to show you that our exponent button is over here. To the second power, sure, I could use this x squared button, but we are going to be doing exponents other than 2. So this is called a caret button. It looks like an arrow pointing up. If you do that, it raises it so it looks like an exponent, and I can hit a 2. But you can see that we do get 32 as our answer. So let's do B and C. And again, I would wish you could do it without your calculator, but of course I want you to know the buttons to push on your calculator. So 8 times 2 to the 0 power. Hopefully you remember that anything to the 0 power is 1. So I really have to do 8 times 1, so the answer is 8. And then finally on C, I have to do 8 times 2 to the negative first power. People mess up negative exponents all the time. We talked about it in September. I would wish that you'd be pros at it by now. That negative exponents really are our fractions, right? Negative exponents, we learned, were the reciprocal of the positive. 2 to the negative 1 power really is 1 over 2 to the first power. And then this is getting multiplied by 8. So honestly, it just says 8 times 1 half. 8 times a half is 4. And if you don't believe me, we take out that calculator and we type in 8 parentheses. Remember our, I want to do 8 parentheses 2 to the negative 1 power. 8 times 2 to the negative 1 power. Hit enter, and I do get 4 as an answer. So that's how we use our calculator. Hopefully it was a good reminder about exponents. And now let's see what happens when we graph this stuff. Before we graph, we do have to talk about D and E, the average rate of change. So notice the words average rate of change. So when we're doing functions that are not linear, we like to call it an average rate of change because it's not a straight line. It will be a curved line. So we can't call it slope, and it doesn't change at a constant rate. So we consider it an average rate of change. But when you do see the words rate of change, we do think about m equals y2. minus y1 over x2 minus x1. And if this is the formula we're using, we need 2 points. And where do we get those points from? Well, it comes from this given information here about the x's. They're telling me use a point whose x value is -1, and they're telling me to use a point whose x value is 0. We just need to figure out what are those y values. Nicely enough, we did it already in a do now, right? Look at letter C. Wasn't the x the -1? So my y is the 4. So 1 point I'm using is -1, 4. And then if we look at letter B of the do now, we inputted a 2. We inputted a 0. So my x is 0 and my y turned out to be 8. So these are the 2 points I'll use the slope formula for, and it will help me find the average rate of change between these 2 points. So the average rate of change would be 8 minus 4 over 0 minus -1, which turns out to be 4 over 1, which really simplifies to be 4. So let's calculate the average rate of change from 0 to 2. That means one of our points has an x value of 0 and the other point has an x value of 2. This do now is probably like one of the most important do nows for future lessons in this unit and the next unit and the next unit. Please know that this average rate of change is very dominant on the Regents exam. We have to be able to find an average rate of change. They will always give us x values, and we need to find the y values that go with it. Again, we already did a do now that helped us find the y values. When the x value is 0, the y value was 8. That came from part B. And when the x value was 2, the y value is 32. That came from part A of our do now. If we use the slope formula, I'll do 32 minus 8 over 2 minus 0. So I get 24 over 2, which actually simplifies to be 12. And something that you should be noticing is that these 2 rates of changes are not the same. So when we were doing the rate of change for linear functions, the rate of change was always the same everywhere on that graph because it was a straight line. We like to say that linear equations have a constant rate of change, but exponential functions do not. An exponential function, the rate of change changes, and it changes quickly actually. It went from 4 to 12 rather quickly. So let's take a look at what an exponential function is in general. So it's written as y equals a times b to the x. A uh, actually represents the y-intercept, and I have it written down right here for you, while b represents what we call the growth factor. Okay, that's my favorite thing to call it, a growth factor. It is a base. It is a multiplying factor because it's a number we multiply by, but it actually shows how quickly exponential functions grow. Sometimes we call it a decay factor because exponential functions can actually decay instead of grow. If a function grows, it's increasing, and if a function decays, it's decreasing. So before we start example 1, I need you to fix yours. Mine is fixed. You, I think, have a negative here in front of the 1. It shouldn't be negative. So you could just turn it into like a positive sign, right? Because it was a negative sign. It needs to be positive. So I want to graph f of x equals 1 times 2 to the x power. So how are we going to graph this? Well, the best way is using a graphing calculator. So if you get that out, in our y equals button, we will put 1 times 2 to the x power. So let's see, y equals, clear out anything that you have there. 1 parentheses, 2, close parentheses, to the, remember this is our exponent button, and put an x there now. Now, honestly, you don't need that coefficient of 1. I wanted it there so that you could see what the y-intercept is, but you could leave the 1 off on your graphing calculator. You know, a coefficient of 1 isn't really necessary to type in. Let's go look at our table of values and copy down whatever information we can. I got to get back to a good part of my table here. Okay, so I want to go to where x is -3, and I see it's 0.125. Boy, awful small, isn't it? And then when x is -2, it's 0.25. And then when x is -1, it's 0.5. When it's 0, 1. When x is 1, it's 2. When x is 2, it's 4. And when x is 3, it's 8. So put those numbers in. And now, how are we going to plot these numbers? Well, some of them are really easy to plot. So I want to plot the easy ones first. I'd like to plot like 0, 1. And how about 1, 2? And how about 2, 4? And how about 3, 8? Now the other points I'm going to kind of estimate. I could see at -1, it's 0.5, which is a half, so I could kind of get that half in there. The other things, though, it's going to get really hard to graph. Do you notice it doesn't go down to 0? Right here, I even want to show you our graphing calculator again. If I keep on scrolling, do you see it keeps on getting to be a smaller and smaller decimal number, but it's not a 0? This up here we'll talk about when I see you. It's like scientific notation. It just never hits 0. Exponential functions always come really, really, really close to a horizontal line. And most of the times that horizontal line is the x-axis, but it never touches it. So when I graph this, I have to get as close to the x-axis as I can, but not touch it, not cross over it. I will put an arrow here, it goes forever, but it doesn't ever touch the x-axis. It can't look like it's curling up. If it looks like it's curling up, I'm going to have to mark you wrong. So be really, really careful. It's getting closer and closer and closer, but never touches. So draw it for as long as you can without touching. So I'm going to go to right about there, and I can label this f of x. So notice how it starts off really slow and then zooms right up. And that's how come we say the rate of change is not constant. So is f of x increasing or decreasing? It's going up. So yes, it's increasing. What is the y-intercept? It is at 1. And remember what we said is that this number here will be the y-intercept. So that's why I wanted to write the 1 in there so that it would stand out. And then it asks for the growth factor, growth or decay. Let's circle growth because it is growing. And the growth factor is 2 because it's that number in the parentheses. Really what it's showing is that for each x I move over, y is doubling, right? That 2 is showing that it's doubling because it's a multiplying factor. It shows that it's multiplying by 2, right? It was 1 right here, and then it was 2, and then it was 4, and then it was 8. Guess what the next one is? Yeah, it is 16 when x is 4. So it's doubling for each x that increases. The domain, remember, are your x values. Notice that there's an arrow at each end. So the domain really is all real numbers, which is -infinity to +infinity. The range is a tricky one. Remember how I said it comes close to the x-axis but never touches it? So it's getting close to 0 but never touches it. So it has to be a parenthesis by the 0. and then it is going forever upward. So when we're doing exponential functions, um, I think this is a true statement. I think I could say that the range will never have a bracket unless like we don't put arrows, unless there's like a closed circle someplace. But if there's arrows at the ends, it actually gets closer and closer and closer to zero and never touches it. Let's take a look at B. Let's put that into our graphing calculator. So I put in my 2 in my parenthesis. Now I need the 1/2 as my base. Don't forget to get a fraction. It's alpha y equals enter. And I could put in my 1/2. Make sure you move to the side before you close those parentheses so that the whole 1/2 is in the parenthesis. And then I have to raise it to the x power. And we'll go look at our table. And we want to put these numbers in. Look at when x is -3, 16, then 8, then 4, 2, 1, then 1/2 and 1/4. So write that down and let's do the best job we can plotting it. So I can't fit -316, so I'm not going to plot that point, but I will plot -2, 8, and -1, 4, and 0, 2, and just be really careful here. It's going to get closer and closer and closer to the x-axis, but it will never touch it. Sorry, the pen I'm writing with, I have a hard time with. Okay, so this is also f of x, and you can see each time it's getting cut in half, and the base was a half. Is g of x, oh, this is supposed to be a g. This is a g. Fix it for me. Is g of x increasing or decreasing? It is decreasing. The y-intercept, you can see it's crossing the y-axis here at 2. We could also see that this is a 2. The decay factor is a half. And I forgot to mention it back when we did part A, that you needed to add this domain and range in. So hopefully you just added it to your notes. For B, we're going to add it also. Again, there's arrows at the ends of this. So the domain is all real numbers, -infinity to +infinity. And the range, how low does it go? Well, it's getting super close to 0, but never touches it. And it's going off to infinity. So it looks like both these functions, one was increasing, the other was decreasing, but they have the same domain and range. Interesting, right? So when we see a function, we should know right away whether it's increasing or decreasing, because hopefully you noticed that when this multiplying factor was a whole number greater than 1, it increased. So I said if b is greater than 1, it's going to increase. But if this is a fraction, it means it's a number between 0 and 1, so that would make it decrease. So I said that b is between 0 and 1. 0 is less than b, which is less than 1. So without even graphing, we should be able to do example 2. So for each of the following exponential functions, give its y-intercept and determine whether it's increasing or decreasing. So the y-intercept is 8. You're also allowed to write it, by the way, as 0, 8, right? The y-intercept is a point. And it is decreasing because 2/3 is the multiplying factor. And 2/3 is between 0 and 1, so it's decreasing. On part B, the y-intercept is 125, or we can name it as a point 0, 125. And the growth factor, notice how right away I just called it a growth factor, is 1.5. It is growing, so it's increasing because 1.5 is greater than 1. And in C, the y-intercept is 56 and is 3 halves, 3 over 2. Is that increasing or decreasing? It is increasing, right? 3 over 2, if I changed it to like a decimal or a mixed number, it's 1.5 or 1.5. So it's actually growing. Therefore, we say it's increasing. And example 3, find the equation of the exponential function in this form. Remember, a is my y-intercept and b is my multiplying factor from the table below. So important when I was telling you what the y-intercept was, remember how I was writing it as a point? So 0, 10. 10 is the y-intercept. So y equals 10 times. Now just look at the outputs. What's the growth factor? It is growing, isn't it? Yeah, it's 3 to the x power. That's it. Okay, so as long as you can find a y-intercept and a growth or decay factor, you can write an exponential function. Remember, it comes from multiplication. Each time here, I multiplied by 3. It's way different than linear functions. And in example 4, which choice would you pick? So I hope you pick choice 2. So let's talk about it. The first thing I look at is the y-intercept. It's right about here. But notice how the scale is not perfect. But I do see that the y-intercept is less than 20. So it can't be choice 4 or choice 3. So maybe it's a 15. Maybe it's an 18. But isn't it decaying? Isn't it going downward? So this 1.25 can't be true. So it has to be choice 2. So my explanation will be that the y-intercept is less than 20. And it's decaying. So the growth factor has to be between 0 and 1. So the multiplying factor, I'll call it. Sorry, my pen again. It's between 0 and 1. And now you can work on your homework. And if you finish that quickly, of course, study for your midterm. And I'll see you soon. See you. Bye.